Greetings class, with this screencast I'm going to teach you a brief introduction to the vapor compression refrigeration system. By introduction I'm going to just present you the idea of refrigeration. Refrigeration means the process of maintaining a system at a temperature below the temperature of its surrounding. As you are aware of what refrigeration is, the sentence itself clarifies what the idea. So, suppose a body is kept at a temperature on the surrounding and you want to reduce the temperature of that body lower than the temperature of the surrounding. That process is called refrigeration. The law which governs refrigeration is thermodynamics law of second, which means basically the closure statement. What closure statement says is that without the help of an external work, you can't transfer heat from a lower body to a higher body. So what it actually means is that in order to reduce a body below the temperature of its surrounding, you need to provide an external work. With the help of that external work, that temperature can be kept below its surrounding. So, this system, that means here I am going to introduce you the vapor compression refrigeration system. Here, the prime mover or the body that provides the work is the compressor. Here, the compressor is used to provide an external work such that with the aid of that work, you can keep the temperature of the body here. Here, the body is evaporator. See, that evaporator temperature is kept below temperature than its surrounding. So, a simple vapor compression refrigeration system consists of basically 4 items. The first one is the compressor. The second one is the condenser. The next is an expansion valve. And the last one, evaporator. So, evaporator is the body where you have to keep the temperature below. As you can see, I have provided a line diagram of a simple vapor compression refrigeration system. See, here is the evaporator, and by starting, let's assume that after the evaporator, the vapor is leaving. That means the refrigerant, or here the working fluid, is actually vapor. Suppose that vapor is actually dry saturated. Dry saturated means the temperature is very much low and it is full of vapor only. This dry saturated vapor, suppose at a pressure P, leaves the evaporator and enters the compressor provided here. What the compressor does is that with the help of, say, an external work, this compressor compresses the vapor from a lower temperature P2 to a higher temperature P3. And what happens is that this dry temperature vapor at this pressure and temperature is drawn into the compressor cylinder. Suppose that it is a reciprocating compressor, and this reciprocating compressor, what it does is that it compresses the vapor during the suction stroke, and during the compression stroke, the compression is happened, and by the exhaust port, it is being thrown out. So this process is actually shown here in the diagram. So this high compression vapor is actually passed through the condenser. There what it does is that it rejects the heat that is being collected from the evaporator, and that rejected heat, after rejecting the heat, it loses its maximum amount of work that is being done on there, and it loses the heat, and that vapor is actually passed through the expansion valve. So after the expansion valve, in the expansion valve, this high temperature and high pressure vapor is expanded and it reaches the evaporator. Its temperature is actually reduced. On reaching the evaporator, that means the heat is being again given to the inlet, and again it changes to its vapor state. This is actually what happens in a simple vapor compression refrigeration system. By this, actually there are 2 characteristic curves that represent the process as a whole, and I'm going to show that on the next slide. These are the basic 2 characteristic curves that is going to Here the 2 characteristic curves are actually the pH diagram as well as the TS diagram. The pH diagram represents the pressure enthalpy diagram, and the TS diagram represents the temperature entropy diagram. As you can see that the compression is actually isentropic. That means the compressor actually does a reversible adiabatic work on traveling from the point 4 to 1. After the compression, what it does is that the heat is being rejected to the condenser. That is being shown here as a constant pressure process, that is an isobaric process. After the isobaric process, what happens is it is passed through the expansion valve, which is an enthalpic process. That means the enthalpy remains constant. Here you can see that H2 as well as H3 both are the same. That means it is on a constant line. After the isenthalpic process, what it does is that again it is an isobaric heat extraction. On the evaporator, what it does is that the heat is being extracted and that heat is being transferred over to the condenser. So you can see that both processes are happening simultaneously. So I can briefly summarize it as the compression is an isentropic compression. The expansion, it is an isobaric expansion. In expansion, it is an isenthalpic expansion. And the condenser, what happens is that it is an isobaric heat rejection as well as a isobaric heat absorption. So, over to the next slide, you can see that COP. COP means coefficient of performance. How you can rate the working of a vapor compression refrigeration system or generally any refrigeration system. Usually for engines what we have is that efficiency. Here what we have is coefficient of performance or COP. By definition, COP means the desired effect divided by the compressor work. For the characteristic curve, basically the pH curve or the pressure enthalpy curve, we can see that the desired effect, that means how much amount of heat we have to extract, that is given by H4 minus H3, that you can see as the first equation. So from the characteristic curve I can state that the desired effect or the amount of heat that has to be extracted is H4 minus H3. Now over to the heat rejection. It is again also an isobaric heat rejection. So here from the maximum of H1 to H2. So the difference H1 minus H2 gives the heat rejection. That is being shown here as H1 minus H2. Next to the compressor. The compressor work I can get from the curve was H1 minus H4. So the equation for COP becomes H4 minus H3 divided by H1 minus H4. Basically for a vapor compression system, the value of COP can actually vary and it can be above 1. Mainly because we have to provide a large amount of compressor work, and with respect to that compressor work, the desired effect will be much higher. It doesn't nullify the effects, it doesn't provide much more difference, but COP of a refrigerant can be more than 1. Now coming to the heat rejected, I can see that actually it will be H1 minus H2. H1 minus H2 is actually the sum of H1 minus H4 plus H4 minus H3 because the expansion is an isenthalpic expansion. That means H2 will be equal to H3. So the heat rejected will be actually the sum of the desired effect as well as the compressor work. With this, I conclude my topic. Thank you.